Hello, I am Pradubhati, and this is a lecture on clustering, which is a common type of unsupervised learning. So in this lecture, we will discuss about the basics of clustering, the principal objective of doing cluster analysis, and we will discuss two common types of clustering techniques. K-means clustering, which is based on partitioning, and a hierarchical clustering, which is a second type of clustering. Within a hierarchical clustering, we focus on agglomerative clustering, which is a bottom-up approach, and divisive clustering, which is a top-down. And we go over some technique involving cluster validation, which is in general difficult to do because there is no one consensus approach. Let's start with the basics. Clustering is a process of finding subgroups in a given data set. The subgrouping is defined based on relationships or some kind of similarity. It is not a prediction method, unlike some of the supervised learning algorithms that we have covered so far, where you have a training data and employ supervised techniques to model. In clustering, you try to identify some structure or patterns in the data using similarities measure, which we will formally define. So the objective is to identify cluster structures such that items or observations in a cluster are more similar than observations outside of that cluster. So effectively, the objective is to minimize a variation within a cluster and maximize the distance between clusters. The similarity is primarily defined using some kind of distance, and we will cover some of the distances used in K-means clustering and hierarchical clustering in subsequent slides. So we need to define how to measure the similarity or dissimilarity of observation. And in general, if we use a distance-based similarity, the larger the distance is, the higher the variation, or the smaller the similarity between the observations. So the two are inversely proportional. So clustering in general is considered exploratory analysis or a type of unsupervised classification. Again, because we don't have a training data set to fit a supervised model. One potential use of clustering is as a precursor for supervised learning. If you don't have a training data set to do supervised learning, we may apply cluster analysis, and each cluster will provide a label and use that as a training set. So that means you can use clustering for aiding supervised learning. So the first thing we do is define a similarity or some measure of closeness of observations. And it follows an iterative approach, and as a result, we have different clustering algorithms that tend to result in different clusters. Okay, but pretty much all of them use some kind of iterative process. As for the clustering algorithm, primarily there are two kinds. One is partitional, which creates mutually disjoint sets, which means an observation can only belong to one cluster, like the one produced by K-means and hierarchical, which identifies nested structure. So hierarchical means a cluster within a cluster, and then we have a slide to discuss that. There is also a third type of cluster. It's not as common, density-based approach, but we're not going to spend a lot of time discussing that approach. Okay, let's start with a widely used clustering type called K-means clustering. So it is a simple iterative approach and is a type of partitional clustering. The objective in k-means clustering is to find partitions of the observations into a preset number of clusters. So the k in k-means represents the number of clusters, and it has to be known a priori. That means before starting forming the clusters, we need to determine the number of clusters. Okay. Again, as I indicated before, the objective is to minimize the variations within a cluster and maximize the distances between different clusters. So what is the objective function we minimize? Here it is in this expression. So this is the objective function, which represents the total variation within each group. Here we take the sum of the square difference of each observation in the cluster, and it is centroid, and we sum over all the clusters, and that is what we minimize. It is a local solution because we are using the difference within a cluster centroid, not every other cluster, which is a large space to consider and computationally intensive. And here, the variation of a single variable within a cluster is measured like this with the sum of squares. Okay, you take the difference between each of the variable, and it is mean value, the bar, and then you average by the number of observations in that group. And the overall variation is a combination of each cluster variation, as we saw in the earlier slide. The cluster result is largely dependent on the variability of the variables, since this is a distance-based similarity measure. Variables with larger variance will dominate the clustering as their contribution in the distance calculation is larger. So to avoid that, typically when we do k-means clustering, we do scale the variables to avoid a situation where a few variables dominate the cluster formation. When we talk about distance-based similarity measure, it means numerical data, because distance calculation for numeric variables is well defined. So the input data for k-means has to be numeric variables. Primarily, the commonly used distance is Euclidean distance, although there are other distance measures as well. Cosine similarity and correlation measures can be used as well. We will cover this in more detail when we discuss hierarchical clustering. So once we go through the algorithm and the iterative steps of defining the clusters, the output is characterized by the centroids, which is a vector of the mean value of each variable for a given cluster. So we will have centroids for each cluster and the assignment of each observation to the respective clusters as output. As I stated, k-means is a local solution and minimizes the objective function we discussed earlier. Here, let's walk through on the iterative process of k-means. We first set the k value, which is the number of clusters. Here in this example, k is 3. Usually, the k values are small for most real-world data sets. So we start with a random assignment of observations. Initially, we assign each observation randomly to one of the clusters, and we calculate the centroids, which is what we are doing here in the first step. So we have 3 centroids representing the value of 3 clusters, the k value of 3. So we have 3 centroids for 3 clusters, represented here by blue, red, and green. Next, we calculate the distance from each observation to the centroids, and then we reassign the observations based on each observation based on its proximity to the centroid, which means an observation will be reassigned to a cluster whose center it is closest to. Okay, so this is what is being shown here. The reassignment is done after we calculate the distance of each observation to the centroid that they were randomly assigned in the earlier step. And next, we recalculate the centroids based on the new assignment, which means the centroid will be moved. So these centroids result, if you compare it from the previous slide, they have shifted a bit, as you can see. Then you recalculate the distances, because now you have a new centroid location, so you would have to recalculate the distances and reassign the observations again based on their proximity with the new centroids. Okay, and that is what is shown here, and then you repeat that step. So you repeat these steps until no centroid's location moves. That means further calculation is not, you don't see any centroid's movement, or no assignment changes occur, at which point the clusters are defined already. So the final result is centroids for each cluster in assignments of each observation to each cluster. As we stated earlier, in k-means clustering, the assignments are mutually exclusive, which means an observation belongs to only one centroid or one cluster. So how do we set the value of k ahead of forming the clusters? In general, that is one of the challenges of k-means clustering. Now, if you have some domain knowledge, it does help, and choosing the right k value becomes a bit easier. But in general, it's one of the difficult aspects of k-means. There are some heuristic approaches to set the value of k. Remember, the objective function we minimize is the variation within each cluster, which means as k gets larger, the variation goes down. And in the extreme case, if we set k to the number of observations, so if the k represents the number of observations you have in the data, each cluster will have a single observation and the variation becomes 0. That's the absolute minimum, right? But you don't want to do that. There are primarily two simpler approaches. One is a direct method, and it is consistent with the objective function criteria, which is minimizing the within cluster sum of squares. We will look at an elbow method, which is a type of direct method. The other one is a hypothesis testing method using some kind of test statistic like gap statistic. So there are two approaches. Let's see how the elbow method works for choosing an optimal value for k. As we said, as we increase the k value, the error goes down. So it has to be a reasonable value, and having domain knowledge helps. The elbow method is a heuristic approach, and it involves plotting the explained variance ratio against the number of clusters. The explained variance ratio is the ratio of the sum of the square distances between data points and their assigned cluster centroids to the total sum of square distances between each observation and the overall mean. So the way it works is, as shown here, you run k-means for different values of k. You start with a small value of k, you can, let's say, start with value of k1 and gradually increase it. For each value of k, you run the k-means algorithm, and you calculate the explained variance ratio, and this measures how much of the total variance in the data is explained by the clustering. And you plot the explained variance ratio against the number of clusters. Okay, this will create a curve that typically has an elbow shape An elbow is a point on the curve where the rate of increase of explained variance ratio starts to decrease significantly. The rate, you see the rate decreases. Like here, because it's coming fast down here, and then you see it is still decreasing, but at a smaller rate and further smaller rate. So these are potential elbow points. So this indicates that adding more clusters is not providing a significant improvement in the explained variance. Okay. Again, the intuition is as the number of clusters increases, the explained variance ratio increases until a certain point. And it is a heuristic method and may not always provide a definitive answer. So that's an elbow method. Here in this example, potentially you could have optimal k values could be 2 right here, could have 4, and could have also 6. So you got to try those different values. Okay. And how do we evaluate the formed clusters? In general, it's difficult and there is no one simple approach. There are some quantitative metrics. You may use a scatter plot to visualize the data points in their assigned clusters. It can help identify patterns and anomalies in the clustering result. This works only if you have a small number of variables. Otherwise, computationally expensive to do it. If you have clusters with very small number of observations, the k value could be too large. So you may consider using a smaller k value. And if you have a domain knowledge and there's some expectation of splits on some variables, you don't see that, then it makes sense to increase the value of k. And if the centroids are close to each other, then the distances between clusters are too small and consider decreasing the value of k. Remember, one of the reason or the very objective function that we're minimizing the variation within the cluster means maximizing the distances between clusters or between centroids. And if that is too small, then you may want to consider increasing the value of k. Those are some general guidelines, but there are also some quantitative metrics, including Silhouette coefficient and Rand index. All right, let's discuss some pros and cons of k-means clustering. Pros, it is simplicity. K-means is relatively simple algorithm to understand and to implement. Another one is efficiency. It is computationally efficient, especially when you have large data sets. It is also scalable. That means when you have large data set, k-means is a way to go. In terms of interpretability, the results of k-means are often easy to interpret as the clusters are defined by their centroids. Cons, it can't handle categorical variables. There are some extensions, but out of the box, k-means cannot handle categorical. That means all the input variables need to be numeric. It has sensitivity to the initialization. Remember, we start the randomly initialized observation to clusters, right? So the quality of the clustering can depend on that initial choice of centroids. And we discussed about local minima solution. So it can get stuck in local minima, lending to suboptimal solution. In terms of outliers can have a significant impact on the clustering result. And also another one is assumption of equal or spherical clusters. K-means assumes that clusters are spherical in similar size, which may not always be the case in real-world data. Another one is a fixed number of clusters. So the number of clusters must be specified before you start the clustering. So overall, K-means is good when the data is relatively simple and the assumption of spherical clusters is reasonable. However, it is important to be aware of the limitation and consider other clustering algorithms for more complex data sets or when that assumption of equal size cluster doesn't hold. Okay, now let's move to the second type of clustering algorithm called hierarchical clustering. It is an algorithm that creates a set of nested structure or nested cluster. It is usually represented as a tree-like structure called dendrogram, shown here. This is a dendrogram. It has nodes and edges and provides a hierarchical structure of clusters, showing how clusters are merged or divided at different levels. In subsequent slides, I'll explain these of dendrogram when we discuss different types of algorithms for forming clusters. Here at the bottom, you see each observation. So these are observations. And as you move up in the tree, you see large subgrouping forming clusters. For instance, 1 and 3 form a cluster, and as you move up, 6, 1, and 3 for a higher level of clusters. And again, we will discuss the details of interpreting a dendrogram. Some advantage of hierarchical clustering includes it doesn't require a specifying number of clusters before you start. It can also handle different shapes and size of the clusters that we just discussed K-means can't do. And some disadvantages are it can be computationally expensive for large data sets, and it can be sensitive to the choice of similarity or distance metric used. And it may produce suboptimal clustering results if the data is not well separated. Again, we will discuss those issues when we discuss the different types of hierarchical clustering. As for the interpretation of dendrogram, so we use horizontal lines that connect nodes to represent clusters. The higher the level of the horizontal line, the more similar the cluster it connects. Okay, these horizontal lines. As you move up in the dendrogram, clusters are merged, and the height of the point where the two clusters merge indicate their similarity or distance. Okay. So yeah, the height is proportional to the distance between the clusters. You can choose a cutoff level on the dendrogram to determine the number of clusters. So all the clusters below that level are considered separate. So in this case, let's see an example using a dendrogram in nested cluster view shown here in these two diagrams. So the orange line here forms two clusters because it cuts the vertical lines twice. And the blue line forms three clusters, indicating by the number of vertical lines it cuts. So in the first one, we have two clusters. Everything following this line, 6, 1, 3, belong to one cluster, and then the rest belong to the other cluster. And you can see the same breakdown here in the nested cluster view. So at this cut level, two clusters, one here, 1, 3, 6, the rest in this bigger circle within the larger one cluster. When you further go down in the horizontal line forming three clusters in this case, then you subdivide that one into two clusters, 1, 3, and another one with a cluster of one observation, which is 6. And on the right, you subdivide that further into two clusters. The cluster containing 2, 3, shown here as well, and the remaining observation in this cluster. And then you continue to do that. And if you have another line cutting right through here, you'll be cutting 4 of the vertical lines. That means you'll be forming 4 clusters. So that is how the horizontal line is used to form clusters. That means, unlike k-means, you only form the cluster once and select the optimal cluster by experimenting with different clusters. You just run horizontal line through the vertical, and then you determine what optimal is. If you remember from k-means, we have to, every time the k changes, you have to reform or reconstruct the clusters. Here, you form the cluster once and select the optimal based on the experiment you do after the fact. All right, now let's start discussing about the two types of hierarchical clustering. Agglomerative clustering, it is a bottom-up approach, and it starts with each data point as a separate cluster and then gradually fuses them based on their similarity or distance. I will discuss similarity measures in the next few slides. Here is the step. So the first step is initialization. So each data point is considered a separate cluster, okay? And then you start merging. That means you calculate the distances, and then compute the distance between every pair of clusters, and then you find the closest pair. So identify the two closest clusters based on their proximity or based on their distance. And then you merge them, combine the two closest clusters into a single cluster. And then you repeat this until all data points are in a single cluster, okay? So that is why it is called a bottom-up approach. You start from individual cluster and then you form one large one. Some of the advantages of agglomerative hierarchical clustering is you don't have to specify the number of clusters, obviously, unlike k-means clustering. So the dendrogram produced can be cut at different levels to obtain different number of clusters. So you can determine, as we discussed in the previous slide, the optimal clusters can be determined after you already formed the clusters. It can handle different shapes and size of clusters, which is unlike the k-means, and it can be visualized using a dendrogram, so that's an advantage. And there are some disadvantages. It is computational complexity. It can be computationally very expensive for large data set, especially when we use complete linkage. And I haven't discussed linkage. This is based on the similarity measure. We have a slide to discuss about what linkage, what distances are used. And another disadvantage of this method is it's sensitive to noise and outliers. Outliers can have a significant impact on the final clustering results. So agglomerative hierarchical clustering is a good algorithm that can be used in various applications for different real-world applications. Okay, now let's discuss about some of the common distance metrics used in agglomerative clustering. For that matter, they are also used for the other type of hierarchical clustering. So Euclidean distance, it is the most commonly used, and it measures the straight line distance between 2 points. So it's just easy to understand. It's just natural. And the other one is Manhattan distance. That measures the sum of the absolute difference between corresponding coordinates. And we can also use cosine similarity, which measures the angle between two vectors. Okay. And Hamming distance measures the similarity between two strings or characters of equal size. Another that is not as commonly used is pairwise correlation, the Pearson correlation, which measures a linear relationship between two variables. I do have another slide to discuss the concepts of linkage that goes with the distance metric between clusters. So the concept of linkage is a way to measure distances between groups of observation, like between clusters, as opposed to simple distances that measure between individual points. And there are different kinds. So there are 4 types. Single linkage is the distance between 2 clusters, shown here, between 2 clusters, and it is defined as the minimum distance between any pair of the points in the 2 clusters. So you have points in this one cluster, other points in the other cluster, and then the single linkage indicators, you pick points that gives you the closest between the 2 clusters. So you just pick points that gives you the closest. The other one is complete linkage, and that is distance between the 2 clusters as defined as maximum distance between any pair of points in the cluster. So opposite to what we did here, you find points that gives you the maximum distance between the 2 clusters. So the extreme cases here. The average one is the distance between 2 clusters, and it is defined as the average distance between all pairs of points in the cluster. So you find the distance of all pairs and you take the average of that. And the other one is a centroid linkage. Remember, one of the results of a cluster is each cluster will have centroids. And then centroid-based linkage is it just defines the cluster distance as the distance between the corresponding centroids. So these are concepts in measuring the distances between groups of observation. Again, it goes with the distance metric used, regardless of what distance metric used for calculating individual distances. This is how you leverage that to measure distances between groups of observations. Okay, now let's discuss divisive clustering. The most common one is actually agglomerative, but the concepts are the same. They both leverage distance metric. So in divisive, it is a top-down approach. Remember, the other one is bottom-up. This one is a top-down approach, and it starts with all data points from a single cluster and iteratively divides into a smaller cluster until that each observation has its own cluster. So the steps, similar to what we did in agglomerative, there is initialization step. So all data points are placed in a single cluster. And then you start the division. That means you select a cluster to divide. And then you do a split, divide the chosen clusters into 2 subclusters, again based on a similarity measure. And here, because we're dividing, it's actually on dissimilarity. And then we update the cluster hierarchy to reflect the new subclusters. And then you repeat that step until each data point is in a separate cluster. Okay. Earlier we said in an agglomerative we merge based on their similarity, and here we divide the cluster based on their dissimilarity. Okay, that's why it's called a top-down approach. Okay. Fuzzy clustering. Until now, the clustering we've been discussing, they deal with definitive membership. That means they provide no uncertainty. Okay. The clusters forms membership that's well defined. In fuzzy clustering, it is a type of clustering algorithm that allows data points to belong to multiple clusters with varying degrees of membership. And unlike the traditional hard clustering methods like k-means, which assign each data point to a single cluster, this one assigns each data point to every cluster with a membership value between 0 and 1, which represents this probability of membership. The key concept here is, so there is a membership function. So that function assigns a membership value to each data point for every cluster. And there is a membership probability. That means the value assigned by the membership function indicates the degree to which a data point belongs to a particular cluster. There are different clustering, fuzzy clustering algorithms that I won't cover here, but here you see this is a probability of each member belonging to a particular cluster between 0 and 1. And if you sum over all those membership values, it gives you 1, which is consistent with the definition of probability. So what we have discussed so far is clustering of observations. We covered different techniques, but they all form clusters of observations. There is another twist in clustering application that involves clustering of variables, which is a technique used to group variables based on their similarities or correlations. Is often used in exploratory data analysis to identify underlying patterns in relationship within a data set. There are generally two main approaches of clustering variables. One is correlation based, and the other one is feature selection based. In the correlation-based clustering, you calculate correlation. So they compute the correlation coefficient between all pairs of the variables, and then you use a correlation coefficient to create a similarity matrix, where each element represents the similarity between two variables. And then you apply some kind of clustering algorithm. Could it be hierarchical or could it be k-means, to group the variables based on their similarity matrix. In the feature selection based clustering, you first use feature selection techniques to identify the most relevant variables. That depends on the task at hand. If you remember from our supervised learning, we discussed some of the techniques to do feature selection. And then you do calculate the distances. So you compute the distance between pairs of selected features. And then again, you apply clustering algorithm, could be k-means or hierarchical, to group the features based on their distances. So that is an application of clustering for variables. And that is it for this lecture, and thank you for listening.